There are an infinite number of ways you can get from a single point to a line. We could start and simplify some of those by assuming we're going to take a straight line path. So rather than wiggling our way in between a point and a line, we'll at least for a start assume that we're going to take a straight line from the point to the line. Now, we could go in pretty much any direction at any angle. And some of them are going to be longer than others, obviously, that makes sense. What about the shortest distance? Now, it might be quite obvious to you that it is the most direct path, and that most direct path will necessarily form a right angle with the line. So the shortest distance is perpendicular to the line. And we're going to use this fact to help us find this shortest distance between a point and a line. Now, quite a key idea here is that this shortest distance lands up at a point on the line we will call x. You could call it anything else, but it's an, at the moment, unknown point on the line. Now, because this point lies on the line, this point will have a very particular structure to it. If this line L is given by A plus lambda B, where A is our position vector from the origin to the line, and B is our direction vector along the line, then the coordinates of x will be A1 plus lambda B1, A2 plus lambda B2, and A3 plus lambda B3. Because all we know about this point at the moment is that it sits on the line, i.e. there must be a value of lambda such that when you take the I ordinates of your position vector and add the correct multiple of lambda of the direction vector in I, you land up on the I ordinate for the point x. And we're going to use this idea to help us generate this shortest distance. So we know that these two things are perpendicular to each other. Well, what two things? The shortest distance is perpendicular to the line. In reality, what we mean is that the vector px now, the vector between p and this point on the line that I've found, x, is perpendicular to the orientation of the line, i.e. the direction vector of the line. And if two things are perpendicular, we know that the dot product between them is 0. So this is what we're going to use to find the shortest distance between the line and a point. So here's a line equation. We've got it in Cartesian form here. You may wish to convert it into vector form if that helps you. And we're told that the point A has the coordinates 2, 3, 4. Even though it's going to be the same diagram as before, I'm quite inclined always to draw myself a little diagram just to help me think about what the problem is doing and visually how I might go about figuring the problem out. So we do need to know the format of x, and as I said, it might be helpful to convert your Cartesian equation of the line, so this one here, into a vector form. So we know that the direction vector lies on the bottom of our fractions. So our lambda direction vector will be 2, 4, minus 2. And our position vector in this case will have been the opposite sign to what's in the top numerators of the fraction. So 3, 2, minus 1. And that is our vector form from that Cartesian form. So x then has the form 3 plus 2 lambda, 2 plus 4 lambda, and minus 1 minus 2 lambda. That is the position vector for the point x. Now we said before that p to x dotted with the direction vector of the line, so 2, 4, minus 2, will equal 0. So we need to go and find px. Well, p to x is the position vector of x minus the position vector of p, which would be this 3 plus 2 lambda, 2 plus 4 lambda, minus 1, minus 2 lambda, minus the position vector of p, which we don't have, but we can quite quickly convert our point into a position vector. That gives us 1 plus 2 lambda, minus 1 plus 4 lambda, and minus 3 minus 2 lambda as our vector px. So we're going to use this idea that the shortest distance is the one which is perpendicular to calculate a value of lambda. So we know that px dotted with the direction vector of the line must equal 0. And we can do the dot product then between these two vectors. Now notice this will give us an equation in terms of lambda, which means we can solve for the value of lambda, i.e. find the specific location of the point x. So we end up with 2 plus 4 lambda minus 4 plus 16 lambda minus 6 plus 4 lambda equaling 0. My mental arithmetic is not quick and probably not very accurate. 24 lambda equals 0. So 24 lambda equals 8, in which case lambda is a third. So this is our value of lambda that we know generates this scenario that we've got going on here. So our point x is occurring when lambda equals 1/3, which is helpful. And what we need is the shortest distance, i.e. the length of the vector px. Well, I have that. That's here. So what I need to do now is substitute in lambda equals 1/3 into my equation for px, which would give me 1 plus 2/3, minus 1 plus 4/3, and 3 minus 2/3, and then find the magnitude of that vector, which is actually a nice-ish exact value, 5√3/3. And this is our shortest distance between a point and a line.